for classification problem. So multi-layer perceptron is well understood. Here I show the input layer. So the number of nodes basically denotes the number of features. And the output, the number of nodes basically denotes the number of classes you want to classify. And here I put the two hidden layer, intermediate layer, and we don't know what it is, but we have a full connection between nodes of two adjacent layers. And when you design the MLP, you need to identify the number of neurons in the two hidden layers. So that's about architecture issues. And that's actually quite challenging. What's the suitable proper number in the neurons? And so, and also how many layers? So you have to try and error to find a good architecture. And once you find that, you initialize the weight, and then you do backward propagation to train a network, and then get the converged result. So this multi-layer perceptron actually is a very important architecture for the artificial neural net, which was popular in late 80s and early 90s. But of course, as I mentioned, there are two main issues. So one is about the architecture design, hyperparameter selection. It's a very ad hoc. So when you see paper, usually they tell you what the architecture look like, but they don't tell you how difficult they get this kind of design right. Another thing is about the theoretical result. So if you have the one layer, one hidden layer, and with many neurons, as many as you want, then there are very nice results about the universal approximation by Sabenko and Hornick, Stinchcombe, and White. So 1989, there are some theoretical foundation. Actually, I think those are very good foundation for the general neural networks. But once you want to go to multi-layer, how to justify this kind of approximation, at least about architecture and about the optimality, about the non-convex organization, it's very challenging. It's very challenging. So it's very hard to understand when you have more layers. So in the first part, I would like to link this to a very classical statistical result, or the classical machine learning result. It's called the two-class linear discriminant analysis. So the LDA. So here I consider if for the convenience of visualization, I use the two-dimensional input. So there is a dimension along the horizontal line X, and there is dimension along Y. So that's easy to visualize. And the LDA basically assume, so there are two Gaussian distributions. So one Gaussian distribution belongs to one class, here denoted by the orange color. Another class, it's a Gaussian distribution denoted by the blue color. So there will be a mean. So the mean will be mu1 and mu2, and also covariance matrix. And the covariance for these two classes, if you want to get a theoretical result, you have to under the assumption they are the same covariance matrix. Okay, so if this satisfied, you are able to find analytic solution about how to do the classification. So basically, you can get a cutting line, and this cutting line has a surface normal W. Okay. And for this side, it's the orange color, and for this side, it's blue color. That's a prediction result. And what the performance look like, it depends on the overlapping of the sample and so on. So this is the cutting line in this case, and you can find the surface normal. It's this form, and also the bias can be found in this form. Okay, so this is a theoretical result, from the very classical machine learning, but how this relate to the MLP? Okay, so that's the question. And so we try to find a link. And so here I want to show you an example, show step by step, how to design a multi-layer perceptron by using a feed-forward process. So instead of doing the BP, instead of making a guess about architecture. We propose a very specific way to design the architecture and also to find the weights. So here I show just an example. So there are two classes, orange and blue, and each class has two Gaussian blobs. So there's two Gaussian blobs here, two Gaussian blobs here. So how I design the MLP stage by stage. So in our design, there are 3 stages. So the first stage is basically it's about the cutting plane. We try to cutting the 2-dimensional feature space, cutting into half plane. And the second stage, we try to do the isolate each Gaussian blob. And the third stage, we try to associate one Gaussian blob to a particular class. Okay, so I will show you how to do that step by step. So the first step, we try to cut the plane. So here there are 4 Gaussian blobs, and we can use the linear discriminant analysis, LDA, to find the cutting line. So we can have this cutting line, and the surface normal is a W prime, and this cutting line surface normal is W double prime. And for this cutting line, we use these 2 neurons to remember half of the cutting plane response. So this neuron, we use the similar color, try to remember the responses in this left half plane. And this neuron try to get a response of this right half plane. And this one actually is because of ReLU in this neuron, so this will be 0. Okay, this will be 0. Okay, and if you don't have a ReLU, this part response will be negative. But because ReLU, you just clip it to 0, and this negative clip it to 0. So one cutting plane, we get the 2 neurons to remember half of the plane. And for this orange color, the same thing, we do the cutting plane here and remember the positive side. So this positive side, and this will be clipped. And this will be the negative side, but we multiply the negative one, this become positive. We do this and give the minus sign here. So this will be positive, and this will become negative. So we remember this part. So one cutting plane, we have 2 neurons. So if you have n cutting plane, then you have 2n neurons. Okay. So now there are 2 questions. So in traditional one-stage linear discriminant analysis, you don't need a 2 neuron. You just have a response, positive, negative, 0, right? You using a response to tell you which side you are. But now, why you need 2 neurons and remember only half plane. Okay, so that's number 1 question. And another question is why you need a ReLU nonlinear activation. What's the ReLU play a role here? As we said, 2 neurons actually try to preserve one side. Okay, so use 2 neurons. You are not able to get both sides if you have the nonlinear activation. But now, what's the role of ReLU? Why you really need that? So here I use these 2 green dots to show so-called mirror points. So mirror point basically is a reflection point across respect to this cutting line. So they have the same distance with respect to this cutting line and the reflection point. So you call the mirror points. So why the mirror points are important here? So basically, this mirror point tells the response. So this part response is positive. This part response is negative. So here we use a y as a response. Okay, after your first stage operation. So this output we call it a y. And y, if you go to the next layer, okay, because at least you have 2 stages. So you go to the next layer, you have the coefficient in the next layer. So this coefficient next layer can be positive, negative. So if y is a positive, okay, if the point is a positive and the weight is a positive, so the multiplication is a positive. Or if the response is a negative, but also the multiplication is negative, they also, when you have the multiplication, you also get a positive. So these 2, they add together. They all contribute to the positive part of this output. And so the danger is that you are not able to differentiate which response. Do you get positive response or negative response? You cannot differentiate because they're all adding together. And then similarly, if you have positive but the weight is negative and the response is negative, the weight is positive, again, you get a negative contribution and they all come together. So you mix up the two sides of the half plane so that if you do the ReLU, you are able to suppress the other side. So it means you only keep this guy, you kill this guy, and another thing is that you kill this guy and you only keep this guy. So you can avoid the confusion of the mirror point effect. So I call this a sign confusion problem. Actually, I studied this problem in earlier days, talk about convolutional neural net, but the MLP here also show the power of the ReLU, basically try to avoid this kind of sign confusion. So once we solve that problem, we look at the second stage. The second stage is to try to isolate individual Gaussian. So you want to isolate that. And the way you can isolate that is first you look who contribute to this guy. So actually, there are two neurons contribute to this guy. So one is this two, one is this two. So they contribute that. But so this I use the red link to show it's one. So we add these two, add together. So but the response will be in this three region. So there will be response here, twice, and then there's some response here. So you have to cancel out this two. And in order to cancel out two, you come down this guy. This guy has the response this one, but you have to subtract. You have to subtract this, and also this guy, you have to subtract this, and this one also being subtract. So you subtract this two. I use this black line to show is a minus p. You want the p larger than 1, so it's more negative. So after that, this 3 will be negative, and only this will be positive. And using the ReLU, you are able to kill that and only keep this guy. And this is just the example. Actually, there is a systematic way to do it. So it can be rigorously done to isolate a Gaussian blob. Okay. In the third stage, actually very straightforward. The third stage, just you have to know, actually in the stage 1, stage 2, we don't need class labels. We only need to know Gaussian blob. But in the stage 3, we need to use a class label. So this part is supervised. So we know this two, one class, this two, another class. So we can combine these two together to this output. And this will be 0 here. And similarly, this two will be get the positive contribution here, and this two be all 0. So in the stage 2 and 3, the link all can be easily designed, either 0, 1, right, in the stage 3, or 1 minus p, stage 2. Only stage 1, you need those linear discriminant analysis. Okay, so, and it tells you how to do things step by step. So this is a summary of the feed-forward MLP design. So you can determine the network architectures and link weights in a one-pass feed-forward version. Stage 1, the half plane partitioning. Space 2, you want to isolate some subspace. And then stage 3, subspace and class association. A neural number, the input dimension is n, that's the feature dimension. The output is the class number. And there are some bound. I look at the neuron in the first intermediate layer, and there are some bound in the second intermediate layers. So this all described in the paper. So at the end, I will give you the reference. So for detail, you can look at the paper. Let me give you more examples. So these are the 3 Gaussian blobs. So we can cut these 3 lines in order to get the 3 half planes. So cut here, and cut here. And then, so the response, you will see something like that. So cutting this line was like that, and then cutting another like that, cutting another like that. So we have the 3 cutting plane, we have 6 neurons. And now we have to isolate that. But now we instead of isolate one Gaussian blob, we isolate half Gaussian blob. So we are able to isolate this half Gaussian blob and using 6 neurons to Gaussian blob and the response. The other response will be zeros. Okay, and then we can combine them together. For example, this and this, we combine to one class. This will be combined in another class. These two will be combined the third class. Another example, a 9 Gaussian blob, we can partition this using 4 cutting lines. Okay. And then 4 cutting lines, we have the A neurons to handle the left and right hand side. So these are the A neurons. So one cutting line here, and one cutting line here, and one cutting line here, and one cutting line here. So A neuron can remember the 8 half planes. And then once you isolate that, you can isolate 9 Gaussian blob using the 9 neurons. Okay, and then eventually you can associate with your class labels. And here I want to compare this with the supporting vector machine. Actually, supporting vector machine only have one stage. So because of one stage, there's no cascade, so you don't need a ReLU. And they partition the boundary using so-called supporting vectors. They want to maximize the margin between the two classes. So the class label is needed, and you want to maximize that, and it's data-driven. The FIT4 MLP actually has 3 stages. So I think the one advantage, because multi-stage, so you need a ReLU. And one advantage of the FIT4 MLP is you can do multi-class classification much easier. SVM, when they do multi-class, they have to do the 1 by 1 versus 1, or 1 versus the rest, those kind of competition. But FIT4 MLP, you can just go through the layer and then eventually go to multi-classes. So there is some simpler procedure to do the multi-class classification. But I want to point out basically is we can use a linear description based on the Gaussian blob, but we can also using data-driven approach to find the linear classifier at the stage 1. So in other words, we can use SVM, a linear kernel, to be the first stage for the FIT4 MLP. And if we do that, actually FIT4 MLP and SVM actually is quite close. They are really like a cousin. They are not really so different. When you look at the traditional BP-based, it seems like SVM MLP is like totally 2 different animals. But when we look at this way, SVM just 1 layer, but the FIT4 MLP is multi-layers. Okay, so now let's go something it's not like a Gaussian blob. We look at more general distribution. So this is called a circle and a ring, but then we have to approximate this ring. The circle is just 1 Gaussian blob. Okay, but the ring we can consider multiple Gaussian mixture model. So here, suppose you have 4 mixture models, and here you have 16 models. So once you get 16, you can approximate the ring better. And then we can follow the design we explained. Another thing is the 2 new moons. This is a new moon. This is another new moon. They interleaved. And here we can use the Gaussian mixture model. Each moon has 2 components. So that's a total 4 Gaussian mixture models. And then this final classification result based on this and based on our FIT4 MLP design. So it's really very beautiful. You can get this FIT4 design, get a very, very beautiful like this. And this is a 4 new moon case. So again, we can consider each one has 2 Gaussian blob, and then do the final prediction. It's very good. But if you hear this, you try to do each moon, do 4 Gaussian blob. But actually, once we do the design, it becomes messier. So it's not like more Gaussian blob will give you better result. Sometimes you give you unnecessary complexity and confuse the final result. So in this case, for new moon case, 2 Gaussian blob per class, per new moon, it's actually better. Some numbers later, okay. So here, maybe people will ask, well, can I do the V4 MLP as the initialization? Okay, I use MLP as the architecture design and also initialization. Then I do the BP. Can I get the best of the both worlds, right? So that's seems a very reasonable request. So we tried and we see three very typical scenarios. So one is 3 Gaussian blob, and then this is the training accuracy, this is the testing accuracy. So 0 is the V4 MLP result, and then we do the BP, how many epochs. So you can see the BP does not change any performance. The performance just stays flat. The second case, this 9 Gaussian blob case, the training is sort of does not change much, but the testing actually sometimes is not very stable. So at some certain epoch, the model, the network model, actually the performance drop by 10%. So that's very severe. So means actually it does not really help and sometimes hurts. And this is another case. It's a 4 new moon case. So in the FMLP is a 0 epoch. And when you do more BP, actually the performance drop, both training and testing. So how to explain this kind of phenomenon? Actually, the conjecture I have is the network we design, the MLP, it's very compact. It's very, very compact. So once you have very compact network, you do the backward propagation, actually cannot see the power. Usually, if you want to really see the power of BP, you have to have a more luxury. You need to make work parameter more, then you can see the effect of BP. But once the network architecture becomes very, very compact, it's just right side. Then you do BP. Actually, it's very hard for BP to find the function. So I think that's our conjecture. Okay, and also show the different initialization. So if you do the FFMLP initialization, and then that's the final result we look. And if you do the random initialization and you do the BP, actually you will connect all this together. So it means you cannot get a very sharp boundary. Again, I think that the problem comes from very compact network. The network size is too small for BP to be powerful. So this is 4 new moon case. Okay, and I think of course here we do the 4 Gaussian component, so it's very messy. If we do the 2 Gaussian component, it will be very nice. In this case, is again, you do random initialization, but it's almost smooth everywhere. You just cannot see those moon shape. Here I want to show you the classification accuracy. So there are different examples, and you can say the bold face is the best performance. So V4 MLP actually in most cases with the very nice result. Even there are something here is very close. Okay, so we do the V4 MLP, the classification accuracy, it's really quite good. Okay, you don't need to do the other backward propagation. So far, all 2-dimensional case. So now we want to show you higher dimensional case. So 4 dimension, 13 dimension, 30 dimension, 8 dimension. And we use a Gaussian mixture model and so on. This is a very realistic data set, and you can see the performance, the V4 MLP perform the best in 4 cases. And this shows the base of the Gaussian blob. You use a 5 Gaussian component or 7 Gaussian component. In this case, actually, is still very close to the best. So it means it works in practical cases, even you do the V4 MLP, to the architecture design, to the weight selection. And finally, I want to show you the time complexity. So the V4 MLP, we consider Gaussian mixture model part, boundary construction, region representation, class assignment, all time, all considered. So you can see the time is very, very small, most less than 1 second, and sometimes 1 second. And here, when you do the BP, it's much, much longer. And also another thing here, this one is a little bit longer time. The reason you use the 4 Gaussian mixture for each new moon. And it takes a lot of time to do the pruning because the boundary is very complicated. the 16, 16 region, and we do, and then we have to prune the boundary. It takes a lot of time. If we do the 2 Gaussian blob per moon, actually is much faster, and the performance is even better. So in general, we can say the V4 MLP give you very small architecture, very small network, and give you very nice complexity, very low, and also very good performance. And now next I will talk about the regression problem. Again, it's approximation issues, right? So we try to approximate generic class of functions. Actually, the way I look at this regression problem is I only need 2 stages. So one intermediate layer, so 1 input, 1 output, 1 intermediate layer. So the first stage from input to the intermediate layer, the interpretation mostly is about the kernel design. It's really about how to design the kernels. And the second stage is once you're given the kernel, then you find the weight and the bias of that kernel. Okay, so this is the 2 stage. And here the kernel design actually can be very generic. So in this work, we try to do is whether we are able to link the regression MLP with the low order polynomial, piecewise polynomial. If we can make the bridge between the MLP and the low order piecewise polynomial, and we know the low order piecewise polynomial actually it's an approximation. You can approximate any function well, square interpretable function, and actually you also know the conversion rate, how fast. That means MLP can do the same thing. So we design spatial MLP, which it's behave like a low order piecewise, low order polynomial. So first, let's look at the MLP as piecewise constant approximator, piecewise constant polynomial. This is well known. Okay, so I don't want to spend too much time on that. So this piecewise constant actually, the basic unit is a box, right? And then you can, given a function, we basically try to approximate piecewise constant. So it's a box. So you can have the box, and then you can use the 2-step function to get this box. And then you are able to choose the weight and to approximate the desired curve. And so we can choose, this is the X, this is the input here, and Y, Yj is the response here, and Z is the output here. So we want to find a function, so this actually is a f of X, is Z, and through this 2-layer design. And so the first layer is our input node. You go to the intermediate node, this Rj, and how to choose this weight and how to choose the offset, you can see. And then you use the step function. The activation function is the step function. And once you do that, and then there is output is from here to here. So that's give the weight according to the something you want to desire to approximate. So this gives you the weight, and this basically gives you a kernel. Okay. Now let's see something non-trivial. So I want to do a piecewise linear approximation. Okay. So how can I get a piecewise linear approximation? Here I use 4 neurons. So there are 2 neurons. It's like a line, but you have the clipping because of ReLU. So here the activation, I use ReLU as activation. So this neuron has the clipping point. This point is xj-1. So this neuron, a positive slope. And there's another neuron, the clipping point is j. So it's clipping this one. So there are 2 positive ones, and there are 2 negative ones. Okay, so the sign is negative. So it's this one and this one, 2 slopes. So 4 neurons, I can design using the blue and the green color. And this is the superposition. So these 2 neurons, you superposition get this one, and these 2 neurons superposition get this one. Okay, and then when you go out, you want to go to the output. Actually, you can use this, subtract this. So this subtract this give you actually it's a triangle shape. It's like a basic unit, and then +1. So there's some offset. But this offset you can subtract when you go the second stage. You can subtract the constant bias, and then you can scale it up to the desired height based on your function you want to approximate. So the first stage is the kernel design. You basically get this kernel. In the second stage, you basically just try to use one, subtract another one, as I said, subtract, and then the bias you can subtract. Each one, you have 4 neurons. Each one has a quarter, and you subtract. Basically, you subtract the constant, this constant one. Okay. So anyway, you are able to get the kernel, and you are able to get the weight, and so on. So first stage, you get the kernel. Second, get the weight and remove the bias, and so on. And piecewise cubic approximation, we can get the activation look like this. This is my activation function. And I need 2 neurons. One is the blue one is the green one. And these 2 neurons, the superposition of 2 neurons, get the compound effect is this red one. So the red one, this is basically the cubic polynomial base, the unit, and also there is a bias 1. So bias I check later when I go to the second stage. And this one, I can give it some scaling to match your desired function. So this is kernel design, and this is the second stage. Second stage, the coefficient basically is the desired value. This green one, green one, green one. And you have to subtract because there are 2 kernels, each one 0.5. So basically, you can subtract 1, this bias. You can subtract that out. So basically, we can construct the MLP that mimic the behavior of low-order polynomials, and the approximation capability of low-order polynomial is well understood. So we are able to provide a constructive proof for the universal approximation theorem, at least for the 1D case. For the multi-dimensional case, I sketch some argument to do that. But the 1D case, clearly, we provide a constructive proof to do that. And actually, the bridge, it's interesting, is related to the activation function. Okay? So if you want to do piecewise constant, you need a step activation. You want the linear approximation, you want the radial activation. You want the piecewise cubic approximation, it's a cubic activation function. So activation actually plays the role of the kernel shape. It gives you the kernel shape. So you will say, well, then MLP just like low-order polynomial. The answer is no. Actually, piecewise low-order polynomial is actually much more limited in its power because the kernel are fixed. Okay, the kernel are fixed, and usually the kernel range, the short range support. So the thing you can adjust based on the parameter, the weights. But the MLP actually able to you are able to choose a parameter in the first and the second stage. And in the first stage, actually, you allow much different kind of kernel. You can use a small compact support. You can use a large compact support. So actually, that's the power of MLP. In our design, we just try to limit the kernel like a low-order polynomial. But generally, the MLP can choose all kinds of the support. So the possibility actually is much more. So MLP actually much more powerful than piecewise low-order polynomial. But here I'm basically trying to say universal approximation. You can borrow the approximation capability of low-order polynomial and to show it also can give you universal approximation. But it can do even more than that. Okay, so now that's about the MLP. Then the part 2, I will talk about the convolutional neural network. And this actually is earlier work. So I don't consider network design. I basically take the Lacan 5-layer network as my architecture. So I just stick to that architecture. So my focus about the weights, how to choose the without the backward propagation and using the feed-forward approach. But in order to do the feed-forward approach, you need some kind of good understanding of what's going on. So the way we look is we want to look at this problem, not the optimization problem. You know, if you do BP's optimization problem, we want to do feed-forward. So we look at this as a dimension reduction problem. So how we do the dimension reduction, and we can zoom into the most important subspace. And doing each layer, you zoom in a subspace. Going another layer, you zoom in another subspace. Dimension going down, but you keep the most important information. And then finally, you try to map that to the desired class labels and so on. So the CIFAR 10 color images, the image size 32 by 32. And if you have 3 color channels, so totally you have 3,000 dimensions. That's your input space. The space is 10, because 10 classes, and we use a 1/2 vector. So if the class 1, you say 1 and 0, 0, 0, and so on. That's training. And then when you do the testing, basically it's softmax. So it's a 10-dimensional output vectors. And we view all the intermediate layers just of various dimensions. And we try to use the dimension reduction process to explain the feed-forward weight selection. And also there is some difference. The convolution layers, in this case, we try to do is unsupervised. We don't use any label information. And then the FC layer, we try to do the supervised. So we will use label information. So convolution layer here, this is the NAFI. There's 2 convolutional layers here. And there's a 3 FC layer, and this is the output. So let's look at this part. So I try to just isolate this and see this part. I can call it like a feature extraction and use a dimension reduction to do the feature extraction. So the convolution operation basis 5 by 5 patch in the NAND, and we flatten it to be 25-dimensional vector, and then we do the convolution. Actually, this we can view as more like correlation. So you try to find a filter, give it a weight to this 25 dimension, and then plus bias, and then nonlinear derivation. And you have the filter K, and in Lacan, Lacan 5, K, the first stage is 6. There are 6 filters. So how to choose these filters? One is you just use the optimization, right? And another we try to consider is a projection on a subspace. And then it becomes a subspace approximation problems. So here, subspace approximation, originally you have the dimension n, so 25 dimension, 5 by 5 patch. And the output is 6, right? You have the 6 dimension a space spanned by the 6 filters. So I put this is like a hypersphere, 25-dimensional hypersphere, and X rounding around in this hypersphere. And I can choose 6 filters as my subspace, span my subspace. And then I can do the projection. You can project to A or you can project back. Okay, so suppose I project everything to X. So this is like, here, let's consider the unit sphere. And so the projection will be cosine theta. So projection can be positive, projection can be negative. And then, the thing ReLU is trying to do is you clip the negative projection, only preserve the positive projection. So I think that's, I started in 2014-15. I have question is why we need this ReLU and why we clip the negative correlation. Okay, so actually the way we look at it is we are able to consider principal component analysis. And this principal component analysis preserve the most energy of the original signal in a low dimensional space. So the first convolution layer is a filter is 5 by 5, so 25 dimension, and output is 6. And we can do unsupervised dimension reduction by principal component, so 25 to 6. And then the second convolution layer, the input is 5 by 5 by 6. Okay, that's the spatial filter size, and this is the channel, because the first put. So the input space 150, and the output is 16 filters. So you have 16 bases to span the subspace. So you want to project to the 16, you can do the PCA to do that. So we can use the PCA to select the coefficient. Okay, so that's the subspace approximation. And also we can decide how many filters based on control by number of PCA. So you have more filters, you can get a better approximation. So now the second question is about the why you clip the negative one. So we use So positive will preserve, negative will clip. So here I show you an example. So this is a 5 by 5. So it's a stripe. So each one is 1 pixel. So it's 5 by 5. And so suppose I have A, my bases look like that, 3 black, 2 white. So this correlation response will be 1, right? Correlation will be 1. This one, the yellow one, is out of phase. So this correlation with this one is -1, out of phase. So if out of phase -1, ReLU will clip this guy, so make a response to be 0. So if you clip all this kind of red, yellow one, will you have any trouble? The answer is no, because this blue box, you can move down. It all has the same phase of this one. Also, this blue shift to the right by 2 pixels. It's also the same as this. So in other words, I don't need this yellow region. I'm able to recover the whole patterns. But if I have this yellow region and give the negative response, actually I'm in trouble. The trouble is the response here is a positive. The response here is a negative. But if I output going is a positive, this outgoing is negative. So positive time positive, negative time negative. They will adding together, and then adding together will cause the output will not know which one is which one is in phase, which one is out of phase. So that's the problem. So this is similar to before, and this I call the sign confusion problem. When you have 2 filters in cascade, the system cannot differentiate positive correlation followed by positive, negative correlation followed by negative. And these positive negative correlations can be just out of phase, right? They are out of phase, and you don't know what's the underlying pattern. Is it 3 black, 2 white, or 3 white, 2 black? So the similarly here. So the ReLU actually play a role. If you look at this like a filter, it's a clip filter. It basically just a rectifier. You remove this case, you remove this case, so that you will know clear what's the underlying pattern it's about. So this is my work in 2016. Actually, it's finished like 2015. And at that time, really, I couldn't find any PhD who want to do this kind of topic. Do it myself and so on. Okay, so now we know we need to clip this to avoid the sign confusion, but then the analysis will become very messy because you don't know which one will be clipped. If X come here, this will be clipped, right? If X come here, and originally you have 6 filters, but you clip some, the dimension just become very small. And so how we try to simplify the analysis? So one way you try to do the subset approximation with argument kernel. So we put this one and this one, both are anchor vectors. So if you do the convolution or inner product, this is positive, this will be negative, it will be clipped. Or this will be negative, this will be positive. So this is like 2 neurons in the MLP design. So we have 2 neurons, and one neuron is a positive, and the other neuron will be negative, and you clip. So it's similar to that idea. But we call the Sachs transform. But the disadvantage is the neuron doubled. So you have original Lanet has 6 filters. Now I need 12 filters. But another idea is that you don't need to increase the number of neurons. You just add some bias. So there is some signal space. You look at the DC, you look at the AC, and you look at PCA is more like AC part. And then you can look at the bias more like a DC. So you add a constant bias for all the filter. And then this constant bias will contribute to a DC term to the next stage. And so you try to have this can be positive, can be negative, but you add something. So this is like a circuit, okay, electronic circuit. You add a bias so that this will be all positive. Okay, and B has to be the same, so that will be easy. It will be DC. This is just a DC component, and then once you add that, then there is no ReLU needed because it's always positive. Okay, this is called a sub-transform, and we can keep 6 filters and plus the bias. And this one is widely used in my research these days. And how to choose the bias? Actually, it's not difficult. Just find all the input X and find the maximum magnitude. This is like Euclidean norm. Okay, and now look at the fully connection layer. You can view this more like MLP, but the key is high dimension. The dimension is very large. 16 times 5 times 5 is 400 dimensions. So cutting plane will be very challenging to do. Okay, so we need another interpretation of this MLP. And so the way we look at this as a clustering problem. We try to clustering them so that the next is a 120 dimension. We try to cluster them in 120 clusters and map each cluster to a unit vector in this 120 dimension space. And similarly here, we try to do clustering and map to one unit vector over the 84 dimension. And finally, we do the same thing. So now we try to do the k-mean clustering, and sometimes we also use the label to help you to do the clustering. So it's a little like label guided clustering. So in the FC layer, we try to look at this parameter is a linear least square regression, and it's a label assisted. We use label to guide the least square regression process. So this is a different dot means a different cluster. So we basically try to look at the target. Suppose you have 10 classes, and then we try to split the 10 classes into each class we split into 12. 10 classes you can split into 120 clusters. Okay, so that's the way. And then we are able to put the 1/2 vector here for the basic unit vector, is a projected unit vector. And this is a feature space, 400 dimension feature space. And this is the weight you're going to solve using the different data. So you can solve this. This will be the filter weight, and this will be the bias. And the dimension reduction, we consider each class, like 0 class, we consider the 12 using k-mean to split the 0 class into 12 subclasses and 1 and so on to total to look at 120. And this try to match Lacan's parameter 120. I feel we are able to reduce this a lot because 0 and 1, they are not really that different subclass. Intra-class variation actually is very weak. So maybe we are able to do each digit, we can only say 5 subclusters. And then we only need 5 times 10. We can choose the 50 instead of 120. So the reason we want to do this subclusters, 0 to split multiple and 1, this is from the ImageNet. So this is a snake. This is another snake. They all have the same class label, but you see visually they are very different. Actually, we look at the feature space, look at deep feature or sub feature. These features are close to each other. These are images with in the feature space they are close. These images are in the feature space they are close. But these two groups, they are not close in the feature space. So that means it's really intra-class variability. The same snake, they have a different cluster. So you need to do this kind of clustering. This is like Gaussian GMM model. So one class you want a GMM. But similarly, here you are trying to do the different clustering to achieve this GMM effect. And similarly here, you have this kind of aqueduct, and these are very close in the feature space. These are close in feature space, but these two are not close in the feature space. And this is also close in feature space. So we do the subclustering and the same label, but do the different clustering so that we are able to get like GMM for this class. So finally, I want to talk about some performance. This is the original NetFi network for the MNIST, but we also try to do CIFAR10, and we needed to incorporate the color. So because of color, I changed the filter a little bit to make the filter a little more. And this is the result, okay? So we do the feed forward, one pass design, the filter weight selection, and then we see the result is 97. And you do the BP is 99. Hybrid basis, the feature extraction, we do the feed forward, but the FC layer, we do the BP. Okay? We do the BP in the FC layer. So we are able to get a better decision module, and this in the middle. Similarly, CIFAR10, we do the feed-forward is 62, and if you do the BP is 68, and the hybrid is 64. The conclusion here, basically I try to say is MLP, we can do the classification job, and then there are different interpretations for each layer. So the first stage, try to do is half space partitioning. Second stage is try to isolate Gaussian blob. And the third stage, you try to do the blob class association. For the regression, the first stage, we can do just two stage, one layer in the middle. The first stage actually try to do the kernel design, and the second stage is the kernel weight and bias decision. And when people do piecewise loaded polynomial, there's no kernel design. They only do this part. Okay, but when the MLP actually, you have the flexibility to do both, so it should be more powerful. A new interpretation of the CAN basically is a convolution layer. We look at it's keep doing the spatial spectral dimension reduction, project to a subspace. This subspace depends on the statistical pixels. Look at the pixels, look at covariance matrix, and we do the PCA. So it has nothing to do with the label. And the FC layer, we try to consider label, and within the same class label, maybe there are multiple clusters because the different shape or different kind of pose or different angle. So we can do clustering. So they're called intra-class variability. And then for each cluster, we can map to a unit vector of a new space. My current research actually focus on successive subspace learning. So you can see the flavor. We try to look at the subspace, and this subspace is the best for your target. Okay. So this kind of learning system, they don't have to be a network. I think the network really, the reason you want a network is for the backward propagation. There's a cost function, and then you try to optimize. But if we want to do the feed-forward explainable machine learning, then you don't need to be a network. Okay, you can be a more flexible architectures. And I want to have a modular design. So each work, you can argue end-to-end advantages, but we can also argue end-to-end disadvantages. So a big machine and something wrong, and how you are going to fix it, it's very hard. Right? Modular design, you can fix it. You can isolate the issue and fix some kind of modules. And so we have some tools like success subset approximation, sub-transform, which we use this a lot, okay? And it's very powerful actually. And can do multitasking because it doesn't have to worry about the class labels. And we also try to look at a successive subset decision. So it's another one stage, right? We want to do the two stage or something. We also look at the subspace success subset generative model, SSG, and we see good results. And I think we can sort of, has very good performance compared to the GAN and so on. And it's all explainable. So we are working on that. And also we using the to handle the 3D point cloud. And we also handle the face recognition and also try to detect the fake video. And this performance also very nice. So we are sort of developing all different kind of applications using this SSL principle. This is the last slide. So there are several references. This is about the sign confusion problem. This is about the SAC transform. And this has a sub transform and the interpretable CNN. And this is the beginning of the talk, two-class LDA to the interpretable multi-layer design. And there is another paper constructing MLP as a piecewise lowered polynomial response. Okay, so I think this slide available to people who are interested. So you can contact the host. You can look at the Professor Ken or Mark, and they can share the PowerPoint with you and so on. Okay, I think let me finish here, and I'm open to any questions. So any questions? Sorry for the very fast speed.
Thank you very much for this illuminating talk. I guess one question would be, I saw the example a little earlier with the pythons, the different snakes that you tested this on. I wondered if you had some other ready examples you could talk about a little bit.
You talk about different snake? You are talking about the snake photos or what?
Yeah. Well, I was wondering if there were other examples you've also tested this against that off the top of your head you might be able to talk about.
Yeah, I think basically all the large data set, like a dog or cat, for CIFAR-10 is very difficult. And usually how we recognize dog or cat, a lot of things, of course, there is an attention model. And again, there are so many posture, so many angles to look at dog and cats, right? So dog and cats, actually, we need a multimodal for dog, a multimodal for cats. The different, sometimes it's because of the posture, but sometimes because of the face. Some face is very clear. So there are different reasons, but human put the label. But if you want to do the BP, CN, they will try to minimize the cost. So through a very magic process to try to minimize the overall cost function, they can eventually link all different things to the cat class or dog class. But if you want to do feed-forward, you don't have that BP to help you. So you really need to think very carefully about what's going on. So because of the clusters, right? But find those kind of clusters actually for the CIFAR-10, this kind of very low resolution image is not easy. Low resolution image, very hard even to see the face. But high resolution image, let's talk about ImageNet. But people say, Professor Guo, you have talked a lot of beautiful things. When can you give me the ImageNet result? If you give me the very beautiful ImageNet result, then I believe you. But actually, there is a challenging. ImageNet, actually, there is attention. You need to find the attention. We cannot look at the whole image. The whole image is too big. So that the CNN deep learning, eventually people realize the CNN really look at the very small regions. That's sort of visualization. That's the place the CNN focus on. The CNN can do that because they use the BP. They find those irrelevant regions, they will just have no effect on the cost function reduction. Only try to do the right thing for that region, you can reduce the cost function. So BP actually very powerful, very powerful. But if we want to do feed-forward, we need to find attention. We need to find which part is really critical for the recognition. So you give us a high bar to do the right thing. So actually, I'm working hard for the last 4 or 5 years in find attention. How to give an images. I try to use age. I try to use segmentation. I try to use all other things, try to find attention. But once I know, I don't need to find one attention. I can find a couple of attention and then see what's here, and so on. So explainable AI, it's challenging. Okay, it's definitely not easy to reach. But I think on the other hand, it really asks us, what do we learn? What do we know? Rather than going through the deep learning and we don't know, right? Just big data, drive the cost function. So yeah, it's high bar, but I feel it's exciting because of this kind of, sometimes we ask, what do we really know? Now, how can we get attention very reliably, right? So suppose a person had a dog, right? So the label can maybe dog only, but actually we should say a person and dog both, right? Humans see both. So attention is a big issue right now, also for languages, right? Natural language processing. So that's the one of big research I'm focusing is attention. How we find the attention, and one image maybe a couple of attention, and then we see what's inside.
It's very illuminating. Thank you. Is there anyone else who has a question? Feel free to virtually raise your hand. Yes, Dr. Sabenko.
Hi, Jay. It's good to see you.
Yeah. Glad you could attend the talk.
Yeah. It's very interesting. Do you have you thought at all about how some of the techniques for explainability could translate to like recurrent networks or transformer networks, so things that work on sequences?
Yeah. Recurrent neural net, it's tougher. Transformer, I'm very interested. Actually, we are working on that. We don't have any result yet, but I think we may have a path. So we really, I have very, very good PhD student, and we work closely on that. And hopefully we can get some good result within the next 6 months. Yeah, so yeah, but it's definitely, it's a very important transformer.
Good, I'm looking forward to reading about that.
Sure, yeah.
Thank you.
Welcome.
Any others? If not, thank you all so much for coming, and thank you, Professor Kuo, for this excellent talk.
Oh, my pleasure, my pleasure.
Thank you very much.
Okay, thank you. Bye-bye.